Our previous video, we did not explicitly model our problem using probability distributions. In this video, we'll see how to use probability distributions to model our uncertainty due to the observation process and our uncertainty in the parameters of our prediction. We also introduced the idea of the likelihood, which is an analogous concept to that of the loss function in empirical risk minimization. The concept of priors is analogous to the concept of regularization. The idea behind maximum likelihood estimation is to define a function of the parameters that enable us to find the model that fits the data well. The estimation problem is focused on the likelihood function, or more precisely, its negative logarithm. For data represented by a random variable x, and for a family of probability densities, probability of x given theta, parameterized by theta, the negative log likelihood is given by L sub x of theta equals negative log of the probability of x given theta. The notation L sub x of theta emphasizes the fact that the parameter theta is varying and the data x is fixed. We very often drop the reference to x when writing the negative log likelihood, because it's really a function of theta, and write it as L of theta when the random variable representing the uncertainty in the data is clear from the context. Let us interpret what the probability density P of x given theta is modeling for a fixed value of theta. It's a distribution that models the uncertainty of the data. In other words, once we have chosen the type of function we want as a predictor, the likelihood provides the probability of observing data x. In a complementary view, we consider the data to be fixed, partly because it's been observed, and we vary the parameter theta. If we look at it in this lens, what does L of theta tell us? It tells us how likely a particular setting of theta is for the observations x. Based on this second view, the maximum likelihood estimator gives us the most likely parameter theta for the data set. The first example that is often used to specify that the conditional probability of the labels given the examples is a Gaussian distribution. In other words, we assume that we can explain our observation uncertainty by independent Gaussian noise with zero mean and variance sigma squared. We further assume that the linear model yn equals xn transpose theta is used for our prediction. This means we specify a Gaussian likelihood for each example pair xn yn by the probability of yn given xn and theta is a normal distribution of yn given xn transpose theta with variance sigma squared. We assume that the set of examples x1, y1, x2, y2, so on, are independent and identically distributed. The word independent implies that the likelihood of the whole data set factorizes into the product of the likelihoods of each individual example. That is, the probability of capital Y given capital X and theta is the product of the probability of yn given xn and theta. The expression identically distributed means that each term in the product is of the same distribution and all of them share the same parameters. It's often easier from an optimization viewpoint to compute functions that can be decomposed into sums of simpler functions. Hence, in machine learning, we often consider the negative log likelihood, L of theta, which is equal to negative the log of P capital Y given X in theta, which is equal to the negative of the sum of the log, the probability of yn given xn in theta. The negative log likelihood, L of theta, is a function of theta. Therefore, to find a good parameter vector theta that explains the data well, minimize the log likelihood, L of theta, with respect to theta. Continuing on our example of Gaussian likelihoods, the negative log likelihood can be rewritten as L of theta equals negative the sum of the log of the probability of yn given xn in theta, which is equal to negative the sum of the log of the normal of yn given xn transpose theta and sigma squared. In turn, this is equal to negative the sum of the log of 1 over the root of 2 pi sigma squared times e to the negative yn minus xn transpose theta squared over 2 sigma squared. Breaking up the product inside the log, we get negative the sum of the log of e to the negative yn minus xn transpose theta squared over 2 sigma squared minus the sum of the log of 1 over 2 pi sigma squared. Simplifying a little bit further, we get negative 1 over 2 sigma squared times the sum of yn minus xn transpose theta squared minus the sum of the log 1 over root 2 pi sigma squared. Sigma is given. The second term of the last line is constant, and minimizing L of theta corresponds to solving the least squares problem expressed just by the first term. It turns out that for Gaussian likelihoods, the resulting optimization problem corresponding to the maximum likelihood estimation has a closed form solution. We'll see more of that when we study linear regression. We have prior knowledge about the distribution of the parameters theta. We can multiply an additional term to the likelihood. This additional term is a prior probability distribution on parameters p of theta. For a given prior, after observing some data x, we should update the distribution of theta. How should we update the distribution of theta? In other words, how should we represent the fact that we have more specific knowledge of data after observing data x? Bayes' theorem, which we previously discussed, gives us a principled tool to update our probability distributions of random variables. It allows us to compute a posterior distribution p of theta and x on the parameters theta from general prior statements p of theta and the function p of x given theta that links the parameters theta and the observed data x. Recall that we're interested in finding the parameter theta that maximizes the posterior. Since the distribution p of x does not depend on theta, we can ignore the value of the denominator, the optimization, and we just observe that the probability of theta given x is proportional to the probability of x given theta times probability of theta. The preceding proportion relation hides the density of the data p of x, which may be difficult to estimate. Instead of estimating the minimum of the negative log likelihood, we now estimate the minimum of the negative log posterior, which is referred to as maximum a posteriori estimation or MAP estimation. The idea of including prior knowledge about where good parameters lie is widespread in machine learning. An alternative view, which we saw in the previous video, is the idea of regularization, which introduces an additional term that biases the resulting parameters to be close to the origin. Maximum a posteriori estimation can be considered to bridge the non-probabilistic and probabilistic worlds, as it explicitly acknowledges the need for prior distribution, but it still only produces a point estimate of the parameters. The principle of maximum likelihood estimation uses probabilistic modeling to reason about the uncertainty in the data and model parameters. When we talk about fitting, we typically mean optimizing model parameters so that they minimize some loss function. The parameterization of a model defines a model class and theta with which we can operate. For example, in a linear regression setting, we may define the relationship between inputs x and noise-free observations y to be y equals ax plus b, where theta is the set AB of model parameters. In this case, the model parameters theta describe a family of straight line functions with slope A and intercept B. Now, if we assume the data comes from a model M star, which is known to us, then for a given training data set, we optimize theta so that M theta is as close as possible to M star, where the closeness is defined by the objective function we optimize. In our example, the squared loss on the training data. After the optimization, that is, when we obtain the best possible parameters theta, we distinguish between three different cases: overfitting, underfitting, and fitting well. Roughly speaking, overfitting refers to the situation where the parameterized model class is too rich to model the dataset generated by M star. That is, M theta could model a much more complicated dataset. For instance, if the dataset was generated by a linear function, and we define M theta to be the class of seventh order polynomials, we could model not only linear functions, but also polynomials of degree 2, 3, 4, etc. Models that overfit tend to have a large number of parameters. An observation we often make is that the overly flexible model class M theta uses all its modeling power to reduce the training error. If the training data is noisy, it'll therefore find some useful signal in the noise itself. This will cause enormous problems when we predict away from the training data. In the diagram on the left panel, this shows an example of overfitting in the context of regression where the model parameters are learned by means of maximum likelihood. When we run into underfitting, we encounter the opposite problem where the model class M theta is not rich enough. For example, if our data set was generated by a sinusoidal function, but theta was only parameterized by straight lines, then the best optimization procedure will not get us close to the true model. However, we still optimize the parameters and find the best straight line that models the dataset. The middle panel in the figure shows an example of a model that underfits because it's insufficiently flexible. Models that underfit typically have very few parameters. The third case is when the parameterized model class is about right. Then our model fits well. It neither overfits nor underfits. This means our model class is just rich enough to describe the dataset we're given. The right panel in the diagram shows a model that fits the given dataset fairly well. Ideally, this is the model class we would want to work with since it has good generalization properties. In our next video, we're going to talk a little bit more about probabilistic modeling and